Okay, and what we do in this clip, we're going to assume that the work done by the external force, the delta W external, is 0. Remember, the delta W external is the external force that's not dissipative, non-dissipative external force exerted. Then we can say that, well, starting with, again, the basic idea that the work done on the system by the net force is equal to the change in kinetic energy. We see that the work done by the system plus the change in kinetic energy is 0. Now this is the work done by the net force. If delta W external is 0, then the work done by the net force just splits into the conservative part and the non-conservative part. And the non-conservative part, since it doesn't have any of this, is the dissipative force, like friction. You can think friction for now if you like. Now the work done against the conservative force is the change in potential energy. The work done against the dissipative force is the delta W dissipative, and that's added to the change in kinetic energy. And the sum of these all has to be 0 because this sum was 0. Now let's just look at some things that can happen. In the first place, the dissipative energy, the dissipative work is greater than 0. The work done by the system against dissipative forces has to be positive. If it was negative, then that would mean that the work done on the system by dissipative forces was positive. And I've just stated, at least, that disorganized energy can't reorganize itself and do work on anything. So since the work done on the system by dissipative forces has to be positive, the work done on the system by dissipative forces has to be negative. The work done by the system against dissipative forces has to be positive. Okay? Again, dissipative forces can't do positive work on the system. They can't have the tendency to increase the kinetic energy of the system. So that the work done on the system by dissipative forces has to be negative, so that the work done by the system against dissipative forces, which is what this stands for, has to be positive. Okay, so this quantity can never increase the mechanical energy of the system. And I've just slipped in a definition on you. Mechanical energy of the system is the sum of its potential and kinetic energies. Okay, so what we can say, if we look at this relationship closely, is that if any one of these quantities, which adds up to 0, is to be positive, for example, if we want to increase the kinetic energy, then this term will be positive. Then since all these things add up to 0, what we get when we add these two had better be negative, so that we get a negative and a positive equal to 0. Obviously, if we've got a positive here, we've got to have a negative here. So that to increase the kinetic energy of the system, the sum of the potential energy change of the system and the dissipative force, dissipative work done by the system, has to be negative. Okay, let's think about exactly what that means. Okay, so again, an increase in any one of the three quantities always decreases the sum of the other two. For example, an increase in the dissipative work done, a positive change in the amount of dissipative work, is going to decrease the mechanical energy, the sum of the potential and kinetic energies. Okay? And to increase one quantity, as I said, the sum of the other two has to decrease. We can rearrange the relationship to say that the change in the kinetic energy is the negative of the dissipative work done by the system minus the change in potential energy. Now again, this is if the delta W external is 0. No work is done by non-dissipative, non-conservative external forces, like me pushing the object. Okay? If that's the case, if we have this, then if we want to increase the kinetic energy, this has to be greater than 0, because delta KE is greater than 0, this has to be greater than 0. Now, if the negative of the delta W dissipative and the negative of the delta PE add up to something greater than 0, what can we conclude? Well, we have to conclude, since the delta W dis is positive, that we've got a negative here. Then to make the sum greater than 0, the negative of the potential energy has to be greater than 0. Not only that, it has to be greater than the negative of the delta, or than the delta W dis. Okay? So we see that the change in potential energy has to be less than 0. The only way this can add up to something greater than 0, since this is greater than 0, is for the delta PE itself to be negative, so that the negative of the delta PE is positive, and that the negative of the delta PE is positive enough to overcome whatever negative we have here. So we say the delta PE has to be less than 0, and the magnitude of the delta PE has to be greater than the magnitude of the dissipative work. Okay, the magnitude of potential energy lost must exceed the energy dissipated. We've got to have enough potential energy lost. For example, the object has to fall far enough to overcome the dissipative energy lost. Okay, another example, delta PE is the negative of the delta W dis minus the delta KE, which says that to increase the potential energy, by very similar reasoning that I'm not going to elaborate on here, but to increase the potential energy, this is negative, so that the delta KE must be negative, so that the negative of the delta KE will be positive, and has to be positive enough to override this negative, so that the kinetic energy loss has to exceed the energy dissipated. The delta KE is negative, so we have a KE loss. It's got to be negative enough to exceed this. Otherwise, the potential energy can't increase.